Okay, so let's talk about kind of number 4, make sure that started off right. So anytime in this situation you've got the total flight time of 4.4, okay, you have to remember that it's going to spend half that time going up and half that time going down. So here's what people typically do wrong. They're going to say, oh, the initial velocity is, they're going to take all 4.4 seconds and multiply that by 9.8, and they're going to get something around 40 meters per second, okay? You have to remember, it's only going to spend half that time going up and half that time going down, okay? So you're only going to use half the time. So your answer to 2 or 4A should be pretty close to 22 meters per second, okay? So what that means is if you draw your position time graph, all you can do is kind of make a sketch. It's going to look something like this. There's 0.200 seconds, and there's 4.4, okay? So the only thing you can do is just make this sketch. But again, here's where this becomes a full circle kind of deal. Is that if you come in here at time 0 and draw that tangent line, that's going to be that initial velocity of about 22 meters per second. So and then as that time goes up, it's going to go to 0, it's going to go negative, and then what lands over here, the slope of that tangent line, going to be about negative 22 meters per second. So you're going to go from positive 22 meters per second to negative 22 meters per second. So on the test, you have to pay attention to the terminology on a question like this. If I say, hey, I want to shoot something up in the air, when does it have its greatest speed? So if I'm just talking about speed, remember that's just the number, it's just how fast you're going. So it has its greatest speed at 2 points. Here where you launch it, here when it lands. Okay, so the speed's going to be the same at these 2 points. The velocities are going to have the same numeric value. This is going to be positive 22, that's going to be negative 22. So on the test, you have to pay attention. Are you asking about speed, or are you asking about velocity? Okay, speed's just the number, velocity has a direction. So the other magic code is when you get to like question number 2. I said, what's the slope of the position time graph at 1 second? So when I ask you this, and I'm going to ask you this question on the test, you mark my words, I'm going to ask you this question on the test. When I say, hey, what's the slope of the position time at 1 second? What am I fundamentally asking you to find? When I say, what's the slope of the position time graph at a particular point in time, you're trying to find instantaneous velocity, okay? Now, with this one, if you think about it, and here's what I got to stress. Don't lose the forest for the trees, okay? So you're starting off in your velocity time graph at about 22 meters per second, and your velocity time graph is going to do something like this. So because I specifically chose 1 second, keep in mind what your acceleration is. If you start off at about 22 meters per second, 1 second later, you're going to drop 9.8 meters per second. Okay? That's what that acceleration means. Okay? So whatever you start with, 1 second later, it's just going to be going 9.8 meters per second slower, which is going to be the slope of that position time graph at exactly 1 second. So that's going to be the magic code. Okay? Hey, what's the slope of the position time graph? I'm not asking how high it is at that point. I'm not asking for the height. I'm asking for the slope of that position time graph, which is going to be that instantaneous velocity. So that's the conceptual part of it. If you're in the equations, you can go, oh, V equals V naught plus AT. Okay? You know your initial velocity is about 22. This is just a y-intercept. Oh, I go over 1, down 9.8 for every second that goes by. Okay? Make sure on number 5 and 6, don't say anything about going backwards. Okay? This says nothing about reverse. This says nothing about reference point. Okay? Don't. All right? Don't. Now, on number 8, okay, so here's your situation, right? On number 8, you've got the two ships, they're both at the same point, they're going to go out and they're come back to that point. So if all goes well on those accelerations on number 8, both of those accelerations should be between -10 and -15. Okay? Somewhere in that neighborhood, that's what those two accelerations should be. Now, let's talk about number 9. I promise you there's going to be a question like number 9 on the test. It's going to be the second to the last question. Okay, I'll tell you exactly where it's going to be on the test. It's going to be the second to the last question. So, here's the setup. So here's Joe Rocket. Okay? Now, don't make this difficult. What's the initial velocity of the rocket? 0. It's sitting on the launch pad. It's not going anywhere. Okay? It's sitting there. So, you can fire the launch pad, you can fire the engines, and here's the whole point of the rocket engines, is to make this thing go faster, okay? Is to make velocity vectors get bigger in the positive direction. That's the whole point of the rocket engine, right? So, page 3H, are my acceleration vectors pointing up or my acceleration vectors pointing down?
Pointing up.
Fantastic, okay? Boom, that's all you have to have. Okay, V1, V2, positive acceleration, boom, you're off to the races. That's all you have to have, okay? Now, the only time, listen to me, the only time you can use an acceleration of -9.8 meters per second squared is if gravity is the only force acting on it. If there's anything else acting on it, you can't use -9.8. Well, the whole point of this rocket engine is to create a positive acceleration, okay? That's the whole point of it. So, you know your initial velocity, you know the final velocity, and you know the distance. There's no time involved initially, so you go, oh, v squared equals v naught squared plus 280. You know the final velocity is 30 meters per second. You know it's to a height of 25 meters. Find the acceleration. So your acceleration should be very, very close to your current age, okay, if not exactly, okay? Because if that's wrong, everything is going to be wrong. So then you're going to use that acceleration to find the time, okay? The time should be around 1.7 seconds, okay? So that should be that value of the time. So what that means is on your velocity time graph, and yes, you're going to have to draw a velocity time graph on the test. So you're going to start at 0, and this thing is going to slope up like this. And at the end of about 1.7 seconds, you are going 30 meters per second. Okay? This is when we're firing the engines. So that's the same idea of me holding this rubber stopper and throwing it up in the air. So when I'm throwing it up in the air, when it's in contact with my hand, that's what's happening in this part of this graph. I'm going to start at 0. I'm going to speed up to about 30 meters per second, and I know how long that's going to take. Now, at the end of that time, I shut off the rocket engines. That's the same idea of me throwing this rubber stopper up in the air. So this is this whole idea of Jedi Stoffelwalk. Stop the force and watch. So, hip, as soon as it leaves my hand, as soon as I stop applying the force from my hand, what's the only force left acting on that rubber stopper? Gravity. What's the acceleration caused by gravity? Beautiful. So at this point, I shut off the engines, okay? So you have to keep in mind that this is a velocity time graph, not a position time graph, okay? So position time graph would look completely different. This is a velocity time graph. So at this point, I shut off the engines. What is it immediately going to start to do? Speed up, slow down. Slow down, because the only force acting on it, like Hip said at this point, is gravity. So this line is going to slope down like this. Now, this is why I said, and you remember this for the test tomorrow, you have to keep a running clock, okay? You have to keep a running clock. So this is about 1.7 seconds. Then you add to that the time it takes for that velocity to go to 0, okay? So you're going to go from 30 meters per second to 0. Now, here's what you have to think through a little bit. Even though this graph is sloping down, is the rocket still going up in the air?
Yeah.
Yes, because it's a velocity time graph, right? It's still going up in the air, but what's it doing? Slowing down. When does it reach its maximum height? Crosses 0, okay? So this is when you shut off the engines. This is when it reaches its maximum height, okay? It's not a position time graph, it's a velocity time graph, okay? Now, make sure that you have labeled the value of the slope of each of these lines in each of these segments, okay? You've calculated them, or you just know what it is. So make sure that you've done that. Now, I didn't ask you to find the maximum height, but if I did, how could you use this graph to find the maximum height? What could you do?
Area.
Yeah, find the area of that whole thing, and there's your maximum height. Okay? I didn't ask you to do that, but if I did, that's what you could do. Okay? So, if all goes well, that total time should be around 4.7 seconds. Okay? So out here at about 4.7 seconds, that's when that velocity time graph should cross 0. Okay? Go with that. Now, on your mini lab, make sure that you've shown all the calculations, okay? Especially how you're calculating that initial velocity. So your velocity time graph should look something like this. And in big bold letters, I tell you to write down the points of your velocity on the velocity time graph, okay? So there's a couple ways you can do this. The easiest is to say, oh, that's a triangle, 1/2 base times height, okay? You know the area because you know how high it went. You know the base, that's half your time. Find your height, that's your initial velocity. Or if you like formulas, you can go, oh, distance equals 1/2 v plus v naught times time. You can do this one as well. It's the exact same math if you look at it. The area of this rectangle, notice it's the exact same thing that this is. Okay? Literally, you do the exact same math. You multiply by 2, you divide by the time. It's the same thing. Okay? It's whether you want to look at it as the formula, or if you go, oh, I like areas of triangles. Whatever works for you. Okay? Anything else at all you want me to go over on that? Yes, Mason?
So the experimental error,
Yep.
can it be negative?
No, it's like an absolute value.
All of it?
Yes, the whole thing is an absolute value. Okay. Anything else? I care.
Number 7.
Number 7?
Very nice.
Okay. So here's the deal. When you're talking about, let's make sure everybody's cool with what I mean by uniform acceleration. If I have uniform acceleration, that just means that it's the same all the time. So uniform acceleration on a velocity time graph is going to be some sloping line. Could be sloping up, could be sloping down, doesn't make any difference. Okay? It's just going to be the same slope. So here, there's 2 ways you can answer number 7. One option is that you draw a velocity time graph and you plot the points on a velocity time graph. And if they're all on the same line, that's uniform acceleration. Okay? That's option number 1. Option number 2 is you go v minus v naught over time. You calculate the acceleration between the different time intervals. And if the accelerations are the same in each time interval, it's also uniform acceleration. Okay, so however you want to answer it here, either one of those is fine. Okay? Comfy? If I win the lottery, I'm going to buy like a really nice like rolling chair with armrests. But you would just probably fall asleep. It's like,
Why don't you have one of those?
huh?
Why don't you have one of those?
What?
One of those armrest rolling chairs.
Oh, because I fall asleep. Middle of a lecture. Workcamp's out. Who's down for the count?
Couches. You can fall asleep while writing on a board, then you can definitely fall asleep.
Oh yeah, oh without a doubt. That's why I don't teach English. That is an honest to God true story. That's why I don't teach English. I would fall asleep reading essays. Oh my God. Yeah. And they wouldn't let me give like multiple choice essays. Like, I'm going to give you 4 essays. Pick the best one and then write 2 sentences about why it's the best one. There, problem solved. Okay, they frown on that. I don't know why. Okay. Now, if you want to hold on to this and hand it in tomorrow, you can. If you're done, and I'll get these graded overnight, if you want to hand it in, I'll get it graded, and you can come in before school or during on-call and pick it up to look at it for the test, okay? So either option is fine, okay? If you want to hand it in, hand it in. If you want to hold on to it, hold on to it. Whatever works for you. Okay. Anything else? Going once, going twice? Seriously.
What?
What?
There's no test.
Huh?
No test.
Tomorrow.
Clayton asked me, I was just clarifying.
I should have told you that last week.
I don't know if
I'm good.
Okay. Yeah, that's tomorrow. And then we'll start forces on Wednesday. So,
Here's a, thing we should do. We should have a test Wednesday, so we go into the weekend. No interviews, just, and we can start fresh the next week.
oh, we're good. The good news is you
I'm
won't
just
have
hoping
your
we
homework
plan-
over the
Plan like
weekend.
that in the future, it'd just be a better idea.
Well, I know, but that's just not how, and I've got like, I kind of have every day accounted for. So, you know,
Just go one day later.
no. Okay, stop that. So the problem that I just gave you, okay, is going to be almost identical to the last problem on the test, okay? I'll tell you straight up how it's going to play out. It's going to be the last problem on your test. It's going to be worth more points than anything else than any other problem on the test, okay? So here's what we're going to do. Here's the setup. You're standing on top of a building that's 8 meters tall, okay? So this ceiling's about 2.5, okay? So you're up there a ways, all right? And you're going to throw a ball up in the air with an initial velocity of 12 meters per second. The ball is going to go up, and then it's going to come, and then all the way back out here on the ground. The ground is the reference point. That's defined as being 0, okay? So you're going to start up here, it's going to go up, whoop, fall all the way down. So everything going up is positive, anything going down is negative. Velocity, acceleration, displacement doesn't make any difference. So here's what I want. So we're going to calculate the time up, you go from here up to its maximum height. The time down, the maximum height, the velocity, impact, and then also the total time. So what I want you to do, right quick, I'll give you about 10 minutes, and I want you to treat this as like being the test question, like this is the test. So what I want you to do is I want you to, if you get part of this work, and you feel good about it, okay? What I want you to do is I want you to come up here and I want you to write the equation. So here's what I want. I want 3 things. So let's say, for example, you're going to calculate, you think you know how to calculate time up. So what I want is the solved equation, okay, for the variable. I want the solved equation for the variable. That's the first thing I want. I don't need to see what equation you start with. I just need to see the solved equation for that variable. Then I want the numbers inserted with the units, and then I want the final answer. Okay? So I want 3 things. The solved equation, numbers, answer. And part of your grade is going to be that you pay attention that G is always negative 9.8 meters per second squared, and you're using displacement. Okay? So, time up, time down, maximize velocity and impact, time total. Now, what you'll also see is there's a whole bunch of different ways that you can solve this problem. Okay, there's probably a dozen different ways that you can solve this. Okay, so if you solve it differently, come up and put that up here as well. All right, Abby, stop that. I'm going to give you about 10 minutes. Okay, so let's kind of start at the beginning. So, Allison, what's my position time graph going to look like? Where's it going to start? Well, is it going to start at 0 or is it going to start at 8 meters?
Zero.
No. We're starting 8 meters above the ground, right?
Oh, yeah.
So it's going to start here, then what's it going to do?
It's gonna go down.
Is it going to go straight down or is it going to go up and then come back down? You remind this is a position time graph, right? So imagine here's the building, okay? I'm going to throw it up in the air, and it's going to do that.
So it's gonna go up.
Beautiful. Okay? So it's going to go up, and then it's going to come back down like this, right? Okay? Now, where's the ball at this point?
Up the highest one.
Maximum height. What's the velocity going to be?
Zero.
0. Okay, so here's the key. And some of you have done this. You basically look at this in terms of 2 flights. On the way up, you're going to start at 8 meters, and it's going to go to some maximum height. And then on the way down, you can view it as starting at 0, and then falling down with some negative velocity. Okay? That's one way to do this. So, on your velocity time graph, Kyle, where's your velocity time graph going to start?
12 meters per second.
12 meters per second, and it's going to do something like this. Okay? Now, let's talk about, Kyle, you did this time up, right?
Yeah.
Okay. Now, this is perfect. Okay? Here's the solved equation, here's the numbers, boom. Now, and again, don't lose track of the forest for the trees. So, since you started at 12 meters per second, okay, page the range. How did I know, before I did any calculations, how did I know my time up was going to be more than 1 second?
Because if it's like if the velocity was negative, or 9.8, then it would have been at 1 second.
Oh, perfect. Okay? Perfect. Remember, an acceleration is not how fast you go, right? It's the rate at which your velocity changes. So what we're saying is that the slope of this velocity time graph is going to be negative 9.8 meters per second. So if you started at exactly $9 or $9.80, like you show up at the mall with $9.80, it would take you exactly 1 second to run out of money. Since you've got a little bit more than $9.80, this time up has to be a little bit more than 1 second. Okay, so before you even get into the problem, step back and think like, okay, hey, what's going to happen? What should kind of happen to my time? Okay, so you're going to start at 12, boom, that's when you're at the maximum height. So this is cool, right? Now, let's talk about maximum height. Who did this one? Okay, Hannah, you did this one, right? So here's the deal. So this is nice, and this is what I liked about this. She solved for this equation. She used that equation, b squared minus b naught squared over 2a. And here's what I'm going to look for on the test. I'm going to look for the fact that she used negative 9.8 meters per second squared here. Okay? Because if she had put positive, she would have technically got a negative displacement over there on the side. Okay? So this is one of the things that I'm going to look for. Do you consistently use negative 9.8 meters per second squared? That's going to be part of the grade on this last problem. Okay? She got 7.35. Now this is where the rules of significant digits play a role. This has 3 significant digits, 7.35. She added that to 8.00. Okay, so technically, she added that to 8.00. Since both of these are out to the tenths and the hundredths, this is why you need to keep that as 15.35. Don't round this to go, oh, I only have 3 significant digits. Because you're adding these, you keep those place values out to 2 decimal places. So what she did was perfect, okay? Now, here's another way that you could have found the maximum height, okay? You could have used your velocity time graph and said, oh, here's 1.22 seconds. I could have found the area underneath this velocity time graph. I was like, oh, I like triangles. Okay? Good for you, Skips. So you could have said, oh, I'm going to take 1.22 times 12 meters per second, found that area, added that to 8 meters. So if you like that triangle thing, you can do this. Now the disadvantage is that you're using 1.22 seconds. And if that 1.22 seconds is wrong, that next part is going to be wrong. Okay? But you could have used the area of the triangle. You also, if you wanted to, you could have used distance equals 1/2 AT squared plus V naught time. You could have used negative 9.8 meters per second squared here. You could have put in 1.22 seconds here and that initial velocity of 12 meters per second. You could have used this as a function equation. But if it were me and I were working this problem, this is what I would have done. Mainly because this is the only one that isn't dependent upon time, and it's only values that are given to me in the problem. But here's the whole key to this story. The more ways you can look at a problem and the more ways you can think through how to solve it, the better off you're going to be. You can say, well, hey, let me try and find that area and see if it matches up with that. Let me try this function equation and see if I get the same thing. Okay? The more ways you can solve a problem, the better off you're going to be. All right. Now, let's talk this velocity and impact. Okay? Now, who did this one? Okay. So, here's what's cool about this. Notice that we have two negative signs underneath that radical. And that would be one of the things that I would look for on here. Are there two negative signs underneath that radical? Now, here's the disadvantage of this. You're taking the square root of this, and you'd have to remember to take the negative value. Okay? You'd have to remember to choose the negative root. But it's cool, it works. Now, here's the other thing that you could have done to find the velocity and impact. Okay? You could have gone to your velocity time graph, and you could have said, oh, V equals V naught plus AT. So the other thing that you could have done is that you could have said, on the way down, okay, on the way down, what's your initial velocity? 0, right? Okay. Plus a negative 9.8 meters per second squared, and then use this time down of 1.77 seconds. Okay? The advantage of this is that because you're multiplying that negative acceleration by that time of 1.77 seconds, you automatically get a negative answer, and you don't have to worry about choosing the negative root. Okay? That's an option. Now, if you're really into slope-intercept, okay, and if you add these times together, you get 2.99 seconds. If you're really into slope-intercept, like, Mr. Burkamp, why was in X plus B? I've got that painted on the ceiling of my bedroom. Weird, but okay. So the other thing that you could have done is that you could have said, oh, my initial velocity is 12 meters per second. So on your velocity time graph, you're starting up there at 12 meters per second. Your slope's negative 9.8 meters per second squared, and you would have put in that total time that's in the air of 2.99 seconds. Okay? So you could have done that as well. But I don't care. If you start at 0, only use the time down. If you're starting at 12, you have to use the entire time that is in the air. Like I said, I don't care. There's like 3 different ways you can calculate that velocity and impact. I don't care. Just pick the one that makes the most sense to you. Now, on the time down, so Macy, you did that one, right? Okay. And this, what Macy did worked. Okay, and I think Hip, you kind of did the same thing. It's complicated, and there's some extra steps, but it works. So Macy found the velocity and impact, and she said, oh, okay, V minus V naught, it's going to start at 0, it's going to land at negative 17.3 meters per second. She knows the acceleration, boom, she finds the time. And that works, okay? Now, what I would have done, if it were me, okay, if it were me, this is what I would have done. I would have said, okay, the ball's up here, and it's going to start to fall, and it's going to fall 15.35 meters. Okay? That's how far it's going to fall. So here's the deal. Here's the deal. What I would have done, and this is just me, I would have gone that distance equals 1/2 at squared plus v naught time. On the way down, what's my initial velocity? 0. So this whole thing drops out. You get 2d over a, the square root of that, you get time. So then, the beauty of this is that it's just one step, okay? But what you're going to have to do is go 2 times negative 15.35 meters divided by negative 9.8 meters per second squared, and you're still going to get that same time of 1.77 seconds. This is, it's only dependent upon using that time down. That one's the way Macy did it, and it works, okay? But she's got to find the maximum height, then she's got to use that to find the velocity, so she's got to use like 2 different calculated values to end up at this. This is just using one calculated value, so the chances of error is going to be much smaller. But here's the deal. I don't care how you solve the problem. If what Macy did, if she does that and she feels good about it and it makes sense to her, hey, that's great. I don't care. You just pick the process that works best for you. Okay, so here's how the test is going to play out. This is going to be the last problem on the test. Okay, it's going to be worth 15 points. It's going to be worth more points than any other question that's going to be on the test. The only thing I'm going to do is I'm going to change the numbers. There's going to be a problem like this on the review. Okay, and so make sure that you work it, and you work it again and again and again until it just becomes automatic. Okay, it's just like, you know, if you're an athlete, you don't go out and do your event one time and go, okay, I'm good, I'll stop now. Okay, you work it again and again and again until it becomes automatic. I write the tests. When I tell you what's going to be on the test, I'm not making it up. Okay, it isn't like I walk in tomorrow morning and I look at the test and go, oh man, I didn't tell the kids that was going to be on there. Oh God, I feel bad. Okay? I write the test. Okay? Trust me. Zoe.
Would you be able to go through the motion diagrams?
Huh?
Would you be able to go through the motion diagrams?
Yeah, like if I ask you to draw the motion diagram on that, so on the way up, you just go like something like this, V1, V2, and then just a negative acceleration. And then on the way down, it's just going to be V1, V2, and negative acceleration. That's all you'd have to do. Okay? That's all you'd have to do. Okay. Speaking of motion diagrams. So let's say there's a ramp, and I'm going to push a cart up the ramp, and anything going up is positive. Velocity, acceleration, displacement. Anything going up the ramp is positive. So I'm going to give the cart a push, and it's going to start with some initial positive velocity. Okay? So as it goes up the hill, what's the cart going to do? It's going to slow down. So what are your velocity vectors going to do? Get smaller or get bigger? It's going to get smaller. So what's the direction of my acceleration vector? Down the hill, right? So my velocity time graph would look something like this, right? Okay? So I'm going to start with some positive velocity going up the hill. Where's the cart at this point? Top. Why? The velocity is 0. It's going to change direction, right? Now, on the way up, what would happen to the distance traveled in each time interval? Okay, what would happen to the distance traveled in each time interval? With the distance traveled in each time interval, maybe it's per second, something like that. Would the distance traveled be getting smaller, bigger, or staying the same? Smaller. Why? It's slowing down, right? Okay? So on the way up in each time interval, you're going to travel a smaller and smaller distance. Okay? Now, once it starts back down, what's going to happen to the distance traveled in each time interval? That's going to get bigger because it's going to be going faster. So in each second, you're going to travel a greater and greater distance. On the way down, okay, you're going to start speeding up because now you're going to have negative velocity and negative acceleration, and you're going to be speeding up. So then your velocity vector is going to get bigger. Now, visualize this. It's rolling down the hill, right? And we're going too fast. But conveniently, we have like a rocket engine, okay? So we're going to fire up the rocket engine as it's going down the hill, and that rocket engine is going to supply a force pushing it up the hill. So imagine this, it's going down the hill, and we fired the rocket engine. We fired the rocket engine, and this thing is going to begin to slow down. We're going down the hill, but we're slowing down. So what's that velocity time graph going to do? Macy. I've got a negative velocity, I fire the rocket engines, and I begin to slow down. So what's my velocity time graph going to do? Is it going to slope up, or is it going to keep sloping down?
It's going to slope up.
Fantastic. Why?
Because it'll be going towards zero.
Because it'll be going what?
Towards zero, because it's slowing down.
Beautiful answer. Okay? So, at this point, I fire the rocket engine, my velocity vectors are going to begin to get smaller, right? So if I fire the rocket engines and these are getting smaller, what's the direction of my acceleration vectors? Up the hill, right? Because that's making it slow down. I get here and I stop, and then I start going back up the hill. That's when that line's going to cross zero. Now remember, what does the slope of a velocity time graph give you? Acceleration. It's cool, right? Acceleration. So if you change, and F equals ma, so if you change the value of your acceleration, what do you have to do? You got to change the force, because force drives the acceleration. So when gravity was the only force acting on it, that was having some negative acceleration. Okay? Then, because I was going down the hill, I fired the rocket engine. Okay? Fire the rocket engine. Now I have this positive force acting on it. Now I'm going to have positive acceleration. Okay? So to change the acceleration, you change the force. Okay? Got that. Okay. So stop that for a second, Abby. Okay. So here's the big ideas, right? First two pages are going to be multiple choice. Okay? I'm going to say, hey, what does the slope of a velocity time graph give you? What does the slope of a position time graph give you? How is uniform acceleration shown? How is constant velocity shown? Okay? What does area underneath the velocity time graph give you? That type of thing. Okay? Pay attention to whether I'm asking about speed or if I'm talking about velocity. Okay? They're related, but they're two different things, right? So if I throw this rubber stopper up in the air, when does it have its maximum speed?
2 points when you first throw it.
Katie, what'd you say?
On release,
And if I catch it at the same point,
when it gets to when it's climbing.
fantastic. Because if it returns back to that same point, you assume that it's symmetrical, where the time up is going to be the same as the time down. I'm going to have the same, if I throw it at 12 meters per second, it's going to land at 12 meters per second in terms of speed. But if I throw it with velocity, it's going to start with positive velocity at 12 and it's going to land with negative velocity at negative 12. So velocities, same magnitude, opposite sign. Speed's the same number. Okay? When it's at its maximum height, what's the velocity? 0, because that's when it's going to change direction. Okay, so those are the big ideas that you're going to need to know. I'm going to give you like a situation. Hey, something's rolling down the hill. Something's going up the hill. Is it speeding up, slowing down? When in doubt, if you get a question like that, and you are, draw your velocity vectors. Okay? Which direction are your velocity vectors pointing? Are they getting bigger? Or are they getting smaller? Is the acceleration in the same direction? Is your acceleration in the opposite direction? Okay? Keep that in mind. let's say, for example, you're going to shoot a mortar up in the air at, say, I don't know, 30 meters per second. Okay, so we're going to shoot this thing up in the air, and then it's going to explode. And I tell you that it explodes, I don't know, 4 seconds later. So I'm going to throw this thing up in the air, I'm going to shoot it, I start the stopwatch, 4 seconds later, it explodes. And let's say I want to figure out the height at that point. So since you don't know what the final velocity is, okay, you can't use that equation because you don't know what the final velocity is. So if I give you a problem like this, and you had a problem like this on your assignment, the only thing you can do is that function equation, d equals 1/2 at squared plus v naught time. You don't know the final velocity, so you'd have to plug in that initial velocity of 30 meters per second. Make sure you use negative 9.8 meters per second squared here. Plug in that time of 4 seconds, boom, there's the height. Okay, that is the only way you can do this. That's it, there is nothing else. And then if I say, hey, what is the final velocity? The only thing you can do that is to do that slope intercept, v equals v naught plus at. That's it. There's no other way that you can solve that. Use this equation first, and then use that slope intercept. Okay? Second to last problem is going to be that rocket problem. Okay? It's going to start at 0. You're going to draw a velocity time graph. It's going to speed up. You're going to shut off the engines. It's going to coast to the stop. You're able to calculate the acceleration, on the way up. Ask yourself when you shut off the engines, what's the only force acting on it? Oh, that's gravity. That's when you're going to use that acceleration. And then the last problem is going to be that ball off the building problem. Okay? I promise you that's going to be your sequence. All right. So here's what I would recommend. You have all your assignments back. Okay? They've all been corrected. What I would do is that I look over those, see if there's anything that you don't know, whatever. If there's any problems, you go, wow, I don't remember how to do that. Okay? Rework it. You're also going to get, as part of the review, a set of review problems, all 10 of them, okay? And the answer keys to this. What I would recommend is that I would lock this away and not even think about it, okay? I just put this away. I'd take this as the test, and I'd work this. Then I'd look at this and use this as like the answer key to grading. If push comes to shoving and you don't have as much time as you would like, make sure that you work number 8. So number 8 is the ball off the building problem. Okay, you're on top of a bridge, you're going to throw the rock, it's going to go up, it's going to come back down. You know this is going to be the last problem on the test. You work this again and again. Maybe change the numbers. Maybe try and find a different way to work it, okay? Phone a friend. Say, hey, Zoe, give me a ball off a building problem. Make up some numbers. Let me try and work it, okay? Because the more often you can work this problem and the more different ways you can look at it, the better off you're going to be on this test, okay? So, there's that. I'm done. You got the rest of the time. So, Abby, stop yonder.